Welcome to today's talk, today's lecture. Today, the main focus will be on photochemistry. So let's start with the content, what we have to cover, and we'll have some initial introductory part, and then we'll slowly jump to the main topic. Okay, so if you look at the syllabus, where you'll find is that the photochemistry actually here we have to cover. These are the reactions. Okay, so cis trans isomerization, we have Norris type 1 and type 2, Paterno-Bucci reaction, photoreduction of ketones, dipymethane rearrangement, you have photochemistry of arenes, and Barton reaction. So can anybody just tell me whether you have gone through any one of the reactions in your previous studies, maybe in your interest, or you have gone through in your undergraduate? Do you have any kind of experience? Any reaction among them? Quickly. Anybody is having anything? Yes or no? Any reactions you have gone through in your undergraduate? Do you have this one in undergraduate? Somebody should respond, because I don't know in this region, northeast region, whether you have or there in your undergraduate or not. Any idea you have? Quickly.
Lourish type 1 and 2, the end of Paterno-Bucci reaction.
So these reactions you are familiar with, right?
Yes, sir.
Little bit you are familiar with. Okay, but I'll be discussing more in details. I think the Barton reaction, this one at least you have gone through, because I have taught this one in your first semester. Yes or no? You
Yes,
forgot.
sir.
Okay, so before going to these particular reactions, let us know some fundamentals of photochemistry. Okay, so whenever you are thinking about a molecule, organic molecule, definitely you know that the molecules are having covalent bonds, right? So you have sigma bonds, pi bonds present in the molecule. Okay, and each molecule, based on its electronic distributions, it has different energy levels. Okay, that you have familiar with. You are familiar with. Now, the energy levels, if we consider, we have generally the electronic energy levels, you have vibrational energy levels, and you have rotational energy levels. Now, the molecule can have some percentage of translational energy too. Okay, generally that translational energies are very, very less. Okay, for a molecule, if you look at the molecule, its motion will not be that much at the room temperature. Rather, what you will see, the molecular electrons, okay, they are not quite stable. Understood? So the electrons can change their positions, okay, even at room temperature. Okay, so if you consider, suppose a diatomic molecule, if you take it, and if you consider the two atoms, okay, they are far apart from each other. When they will approach to each other, okay, what will happen at certain point? They will make the molecule, right? For a diatomic molecule, I'm talking about diatomic molecule. Okay, diatomic molecule. So they will make a bond at certain point. So you will have a new compound formation. Okay. Now, if you look at the change in energy, okay, energy. So energy in terms of potential energy. Potential energy. So what you will observe actually, if you try to look at, so say suppose their potential energy at the beginning was here, and this is the scale of energy, okay, increasing. You have two atoms, right? You have two atoms, one atom is here, another atom is, say suppose here, this is the distance, okay. So at that situation you don't have any uh, interactions between the atoms. So what you will see is they will have their individual potential energy, and you will have a uh, altogether the additive potential energy will be, say suppose at this height, okay, I'm taking the height here, this is the measurement. Now suppose this atom is moving towards this atom, so what will be the situation of the overall energy uh, due to that movement? What we say is the energy is going to decrease, okay, and it will be minimum at a certain point, okay. So when this will reach at this stage, it will be minimum, and then if it moves further, so now this is the distance between the two atoms, and when it will move further, what we see, the energy is going to rise, okay, the potential energy is going to rise, right? So this distance, then we call it, it has made a bond between them, it has formed a new molecule. Now if you further try to make them closer, what you will see, you will have a repulsive force between the two nuclei, okay, and that's why the energy will further rise. So you have initial attraction, it will be a minimum, and then it will rise, okay. Now this we can, I mean, represent any molecule in this potential diagram, okay, and you know this diagram is called as, can anybody tell what is the diagram? This is Morse potential diagram, right? Now what we understand here is when the two atoms are far away, they don't have any bond formation, but when they are coming closer or their distance is decreasing, slowly it is making the bond, okay. Now you think in a different way. Suppose you have a system where the two, weight, they are connected with some sort of string, I mean, or one rod, and if the same ball species, they are connected with bigger rod, what you will see is, if you try to look at the vibration, okay, if we try to do the vibration, which one will do or vibrating more rapidly? Can anybody tell between these two? Quickly. Am I audible to you?
Yes, sir.
So which one is going to vibrate more rapidly between these two?
Second one,
Second
sir.
Second one.
one, sir.
Okay. Now that is the thing. So what we can do now, this potential curve, we can split into different vibrational energy. What it means is, if you have more potential, okay, you can compare with the more vibration, okay, and that is related to the distance. So you have more distance here. If you look at here, it is flat. That means you don't have any kind of interactions between the two atoms. They are far away, okay. So their distance is more. Distance is more means you have more vibration, and vibration in such a way that it has been ruptured the two, I mean, the whole system, and two atoms became individual entity, okay. So they went apart from each other, and any kind of interactions has been vanished, okay. So what we find is that with the increase of bond distance, the vibration is increasing, okay. So this one we can tell, we can present in one energy state, okay. One energy means one electronic energy state. So your electron distribution, ultimately what is happening, you have two electrons, okay, two electrons, they are coming closer or they are going away when you are talking about the breaking or making the bond, okay. Making the bond, they are coming closer, and breaking the bond, they are going away, okay. So ultimately your electrons are changing their positions, their distance between them are increasing, okay. Now this is the situation for diatomic molecule. Now you know already that one system, one molecule, you may have different type of transitions, right? And in your spectroscopic class, you have been familiar with that. So for a certain molecule, you have sigma electrons, you have pi electrons, you have non-bonding electrons, right? According to your situation. Now, based on that, you can have sigma sigma star transition, okay. So suppose you have HCl gas, okay. Now at room temperature, it is fine, you have just the sigma bond. Now somehow if you increase or if you excite this molecule, you may have sigma to sigma star transition, okay. Now that we can represent like excited state. So this and this, you have the difference is their energy, okay. The molecule is same, you have the change in energy, okay. So this is we call one energy state, and this is we call having another energy state. So you have multiple energy states are available, electronic energy states are available. Why we are calling it electronic energy states? Because your electrons is jumping from one orbital to another orbital. Okay, so you have sigma to sigma state is jumping. Getting, so you have multiple energy states are available. Now, what we can do is we can have these electronic energy states, I mean, in terms of Morse potential diagram. Okay, so let us consider this is one electronic states. Okay, electronic states, energy states. This is another electronic energy states. Okay, now when you go for lower energy states to higher energy states, generally the difference is what you will see, since the potential energy is whatever you have here, here potential energy, these energy states will have more potential energy, right, with respect to this one. And if you have more potential energy, generally the ground state vibrational energy what we are talking here, okay, they will not have of same energy. Okay, so their energy will be different. That means you have the potential wall that will be more, I mean, more wider in case of the higher energy states. Okay, and it will be narrower in case of lower energy states. Now, why I am talking this one, it has all meaning. Okay, and it will be a bit clear after a while. Now, you can stimulate any molecule by two types of energy. Okay, one is you can externally give the thermal energy. Okay, and if you give thermal energy, what can happen? The molecule can have more vibrations. Okay, and if you have more vibration at certain point, the molecule can undergo bond rupturing process. Okay, now the same thing we can do in terms of I mean, by using light. Okay, now here actually, if you consider, say suppose CH bond. Okay, the CH bond, you have bond energy is equal to, suppose I think 95 kilocalorie per mole. Okay, now this bond, this much energy we can have the corresponding the wavelength of light required to rupture this bond. Okay, so that can be calculated. So if we put 95 and take the Planck constant and the velocity of light for 1 mole or Avogadro number of molecule, we can easily calculate the lambda, and here the lambda will be around 300 nanometer. So that means if you have light with energy 300 nanometer, okay, or a bit more energy, you can break the bond. Are you getting? So that much energy is there. If you have more energy, you can easily break the bond. Okay, so what happens is the molecule can absorb the external energy. Okay, so here what we'll see is when you are applying the external energy, particularly the light energy, you will have multiple process to occur. Okay, Now that is being represented by Jablonski diagram. And now what Jablonski diagram tells is very, very interesting. Okay, and that will tell you when a molecule is or will be photoactive and when a molecule will not be photoactive. Okay, now the photochemistry you can access or you can achieve only by those molecules which are light sensitive. Okay, now one thing you have to remember that any molecule which absorb light in the sense I'm talking about, you have 200 to 400 nanometer, not 400, 800 nanometer. Okay, 200 to 800 nanometer. That's the wavelength which is responsible for electronic transition. Electronic transition. Okay, now if a molecule absorbs the light within this scale, it doesn't mean that the molecule will be photoactive. Okay, light absorption doesn't mean the molecule will be photoactive. Now if you look at the Jablonski diagram, it will be clear to you. When we consider a molecule at its ground state, okay, generally you have the molecule with spin multiplicity is you have singlet, so 2s plus 1, okay, it will be 1, so it will be singlet. Okay, so it is ground state, you have the singlet multiplicity, so that is the state of the molecule. Okay, now this molecule, when you are shining light, what is going to happen? You will have different electronic transitions. Okay, now this blue color, if you look at, these are the electronic transitions happening. You have the absorptions. Okay, so molecule is going to its ground state, singlet state, to the excited singlet states. Okay, according to the photochemical transitions, the law of Frank-Condon principle, you know, there should not be any change in its nuclear distance during this electronic transition. It is so fast that we don't see any change in the molecular, we don't see the molecular change, geometrical change. So there will be no change in nuclear distance. Okay, so what is happening? It is just absorbing the light, and it happens around 10 to the power minus 16 seconds, so fast. Okay, the most rapid process, this one. So it happens, so it can go to its excited singlet state, S1 or S2, whatever is available. Okay, and then things happen. Okay, so it will try to come back to the ground states. Okay, now this ground state process, you know, when it is coming back, it can have multiple routes. Okay, so say suppose it is as S2, so it can quickly come back to S1, and then it can come back to S0. Okay, now this process happens coming back from S2 to S1. Okay, so this involves the internal conversion process. Internal conversion, this means it is being transferred from same spin multiplicity states. Okay, so you are S to S, so that's what you call internal conversion. So it is coming higher singlet to lower singlet. Okay, and this process happens. What is the mechanism? It is just coming by dissipating or releasing heat. Okay, releasing heat is one of the easiest way for a molecule to come back to the lower states. Now this process, how it happens, let me explain. You have different energy states, right? So as I told, you have say suppose this is S2. S1 will be lower than that. Okay, so you have S1 here. Okay, this is the S1. Now when the molecule has jumped from S0 to S2, say suppose, okay, now you have different small gap, okay, vibrational energy available. So what it will do, it will quickly come down to the next vibrational energy levels, and this way it will just release the heat, okay, because the change in vibrational energy levels is associated with heat. Okay, as I told, like if you apply more heat, you will have more vibration. Remember that one. So that means when it will come back to lower vibrational energy, it will try to release the heat, okay, to the surroundings. Now in this way it can happen, it can come to a situation where same vibrational energy, say suppose this one, is matching for S2 as well as S1. Okay, S1 and S2, they are having the same vibrational energy, this one. When it will reach to this one, it will immediately sliding down to the S1 state, okay? And then it will come back to the S1 ground, okay? The V0 of S1. Got it? So this way it can do the internal conversion, okay? And this process relatively faster, I mean the slower than the electronic transition. So it happens, okay? And when it reaches to the V0 of S1, what can happen? Either it can come back to S0. If you see here, it can come back to S0. So S1 to S0, this is one signature here, and this yellow is another one, S0. Okay, so you have two processes. It can come back to S0 again by the same mechanism. Okay, suppose S0 is also here. So what can happen if the vibrational energy level, if you have a common one, it can again sliding down and it can still continue to decay to the S0. Got it? And this way you can have heat dissipation or heat release, and the molecule can come back to the ground state. Okay. Now another route of coming back to the ground state is it can jump from S1 to S0 without releasing heat, rather it will release the light as energy. Okay. And in that case, we call the system is, this process we call it as a fluorescence. Okay, so it is releasing the light. Now we can understand from here one thing is that if your S1 and S0, okay, they are having enough gap between them, what you will see is that they have very little chance of having the same vibrational energy matching. Understood? So the V0 or some Vn of S1 is matching with some Vn of S0. That may not happen, okay, if you have the S1 and S0 is far away. In that case, you have, since the molecule has to come back to its ground state, so it will jump directly from V0 of S1 to some Vn of S0 by releasing that much energy as the light, okay, the wavelength. Got it? Now another way is it can sliding down to its T1 state, means triplet state, okay, and that can happen if the triplet having some vibrational energy level matching with the S1, okay, the vibrational energy, one of the vibrational energy of S1. In that case, we generally see the sliding of the excited state molecule, okay, coming back to the T1. So it is jumping from S1 to T1. So your spin is changing, and that's why we call this is inter-system crossing. So when it is coming from S1 to T1, we have the inter-system crossing, and then it can again come back to the V0 of T1, okay, by releasing heat, and finally T1 to S0, okay, again by two mechanisms, either by heat dissipation or by releasing light, okay. So these are the process. Now this S1 to T1 and T1 to S0, these are the process changing the spin multiplicity, or involving the spin multiplicity, okay, change in the spin multiplicity, and that transitions are generally forbidden, and that's why that process are far slow, okay. And what we see is that T1 to S0 transition, that process is slower, and we see the energy what is releasing is prolonged, its time is prolonged, and we can see the light quite long time, and that process we call it as the phosphorescence, okay. So this is the overall process can happen for one excited molecule to come back. Now you can easily understand why some molecules are photoactive and why some molecules are not photoactive, okay. Is it clear to you why some molecules are photoactive and why some molecules are not photoactive? Can anybody confirm? Is it clear to you?
Yes,
No,
sir.
sir.
Okay. Now, one thing is that when you have the absorbance or absorptions of light, what we see is that the S0, from S0 to some higher S or Sn, it is being excited. But when we talk about the emission, okay, light emission, what we see is that that can happen always from the lowest excited state, and that is the rule of photochemistry. One of the rule, we call it the Gazi's rule, okay. So it has to come, excitation or emission of light can happen from S1 to, so according to the Gazi's rule, what we find is that the emission will take place from the lowest excited state, that is S1, to the ground state, okay, S0, or the lowest excited state T1 to the ground state S0, okay. So that is the Gazi's rule that generally associated with the release of light by the excited molecules, okay. Now from here you can easily get one information that the absorption spectrum, what you have seen, okay, UV absorption spectrum, say this one, so it is absorbing light S0 to some here, okay, you have different light absorption here, and you have emission is happening here. So it is just the opposite, okay. And if you take the the spectra for the molecules having fluorescence property, if the molecule is absorbing like this way, so your fluorescence will be in the same way, okay, it will be similar way. So you'll have difference in the wavelength, okay. So it will be red shifted because you have the distance here is energy gap is lower than the absorbance, okay. So if you have lower energy gap, you have more redshift. So this is one of the important phenomenon for the molecule, okay, we need to note down. So what we can conclude from here, that the molecules which shows fluorescence or phosphorescence, those molecules are photoactive. The molecules which do not show the fluorescence or phosphorescence, those molecules are not photoactive. So this is one of the important point you should remember. Now, if I summarize quickly all the process, what we can write is that, so S0 state, if you put light H nu, it will go to some higher excited state, some Vn, okay, vibrational energy. Then what can happen from S1V, it can come back to S1V0. So let me write here Vn, and this is V0, okay. And during this process, you have only vibrational relaxation, we call the vibrational cascade, okay. You have the heat is being released. You can have then S1, okay, V0 to S0 Vn, okay, or V0, whatever it is, and that process involve the light emission, and we call it the phosphorescence. We have another route is S1 to S0 via heat dissipation, that you came to know. So that we call it the internal cross conversion. And you can have S1 to T1, some Vn, okay, sliding. So you have intersystem crossing. So T1 Vn to T1 V0, that can happen. So by heat dissipation. So it is again the vibrational relaxation or vibrational cascade. Okay, you can have T1 to S0 by heat dissipation. So here you can write T10 to S0, some Vn or V0. That we call it that as intersystem crossing. Now one important route, another is other type of route is you can have some energy transfer, okay. Suppose you have another foreign molecule is there, okay, at its ground state S0. What can happen is that this S1 which you have excited, okay, undergone excitation, that can come back to S0 by transferring the energy, got it, and the foreign molecule can undergo excitation, got it. So that can happen, and this is, since it is S to S conversion, so we call it singlet transfer, energy transfer. This process we call photo sensitization. And another process is you have, suppose your excited molecule is at T1, okay, triplet state, and you have a foreign molecule which is at ground state. So you can have again energy transfer, and your excited molecule can come back to the ground state S0, and the foreign molecule can be excited to its triplet state. Okay, so this is quite interesting and very informative and usable. Okay, now we'll look into why I have told this one.
Sir,
Yes.
cascade means what?
Cascade means one after another, one by one. Understood? I mean,
Yes, sir.
stepwise. So what we are saying is, if you look at the transition is happening in this case, right? So small transition. So as I have shown here, so it is suppose it is here. Okay, can you see this?
Yes, sir.
It is coming from
Yes,
here
sir.
to here, then here to here, then here to here. So these are the process we call it cascade. So cascade means it is changing its vibrational energy levels within the same electronic states. Okay, got it?
Okay,
So
sir.
that is the
Yes,
process.
sir.
And if the vibrational energy levels are matching of excited state and the ground state or some lower energy states, then it can slide down to the lower excited states, I mean lower energy states. Got it? Now, suppose you have one photosensitizer, okay? So that is at singlet state. I can write this is singlet because they are opposite spin. So this is singlet. If you put light, it got singlet excitation. So I'm writing S1. Good. And then this S1, it underwent intersystem crossing. So you have T1 here. Okay. And then this one is interacting with one acceptor. So acceptor, it is S0. This is S0. Okay, and this is T1. What is happening? The S0 is becoming here, acceptor is becoming triplet, and this one is becoming singlet again. Okay, so what it was at its initial stage, it came back to its initial stage. So what we can tell is this is doing this, it's sensitizing the acceptor A, and in other way we can call this is the photocatalyst. Understood? So it is transferring the energy to the another molecule. Okay, and now when the acceptor got excited, okay, triplet, what it will do, it can do many reactions. Okay, so this is the idea of utilizing photosensitizer. Now say suppose I have a molecule butadiene 1,3.
Sir,
Yes, tell.
sir, can you explain once again this one?
What I'm telling is you have one molecule
Third time, sir.
which is photoactive, right? You have one
Yes, sir.
molecule which is photoactive, and you have another molecule which is not photoactive. Got it? Now
Yes,
you
sir.
can use light to excite the photoactive molecule to its triplet state, and then you can do the energy transfer from triplet state to the non-active molecule. Okay, and non-active molecule can now gain its triplet state. If you directly irradiate, so what I'm telling is, suppose you have this one S0, okay, you cannot make with light this one, okay, T1. This is suppose not possible, but you want to generate this one, then how will generate? Got it? So this is how we generate. We use one sensitizer which is photoactive with suitable triplet state energy, and we excite the molecule, and then we allow to do the energy transfer from one molecule or sensitizer to the molecule of our interest. And then we can gain chemistry, photochemistry from the molecule of our interest. Okay, so are you following what I'm telling?
Yes, sir.
Now it will be more clear. I'll come to the example, then it will be, you will find the interest there. So here I have taken one example, butadiene. Okay, so the butadiene, you have S0 in ground state and you have S1, right? Excited state. Got it? So here, what kind of transition you can tell? Who can tell? What kind of transition you can have? For this molecule? This is S0 to S1. So S1 is what and S0 is what? What is the actual transition? Who can tell? Electronic transition. What is the electronic transition? From which orbital to which orbital?
Singlet to singlet.
Singlet is singlet. This S means singlet only. I am talking about the electrons at what orbital? Orbital level. This is, you have the pi cloud only. So you have pi star transition. Understood or not? So in the ground state, you have all the electrons at the pi bonding, and in the excited state you have the electrons in its pi anti-bonding. Got it? So here what I can write is, this is the excited state. Okay, what is the transition? Pi star transition. So changes is happening from here to here. Okay, this is what you have, the electrons in its pi star orbital. Here you have electrons only the pi. Okay, here you have electron pi as well as pi star. Got it? Now this singlet state S1, excited state, and this is S0. What is the energy gap between them? You have 107 kilocalorie per mole for butadiene. Okay, the triplet energy state, excited state, I mean triplet T1, what is the energy? I mean here from ground state, the energy, I mean it is the 60 kilocalorie per, okay, 60 kilocalorie per mole. So you have the differences between these to these. It is around 48, right? 47.6. Did you get it? So the singlet to triplet, this distance is quite far away. Got it? So, and since these are, if you shine light, you cannot access the T1 easily only for this molecule directly, because what it will happen, what we do generally, if you do excitation according to Frank-Condon principle, it should preserve its spin multiplicity, right? So it should go from S to S transition. So this transition is not allowed. It will not happen. Now what can happen from S1 to, it can come to T1, then T0, then S0, or S1 to S0 directly. Okay, S1 to S0 directly. But what I'm telling is, this gap is quite more. So that's why we generally don't see the vibrational energy level are matching for T1 and S1. So that's why that S1 to T1 transition not, I mean, it doesn't happen for butadiene. Okay. Now let us look at the benzophenone. What we find is that the benzophenone here, you have 74 kilocalorie S1, S2 is 100 kilocalorie, and T2 is 74, and T1 is 69. So S1 74, T2 is 74. It can easily slide down from S1 to T2. Yes or no? After excitation. Are you getting? Then
Yes.
from T2 to T1, it can come down because you have 74, 69, they are very close. So ultimately, it can come down to lowest excited triplet state, okay, for benzophenone. Got it? Now this is 69. What is here for butadiene excited triplet state? 60. So if we use benzophenone, what is going to happen? Benzophenone is providing one triplet energy state just above. This is the benzophenone, okay, from benzophenone. So this is 69. So this is 60, just above the T1. So in that case, butadiene is not getting excited. Rather, benzophenone is absorbing the light, getting excited, coming back to the T1, and this T1 is closer to this T1 of butadiene, and it is higher than the T1 of butadiene. What we will see is that this energy transfer is possible. Got it? And that's how we can have the access of triplet state T1 by using benzophenone. Okay, and light. Are you getting the point? Is it clear to you? Is it clear to you?
Sir, this benzophenone is used this
As the
butadiene.
light, yes. Butadiene you cannot excite. I mean, it will absorb light, but you cannot have its photophysical property. Understood? I mean, you cannot have fluorescence or phosphorescence because you have the S1 and S0. They are very close. I mean, it can easily dissipate, and it can, I mean, heat can be released and it can come back. And it cannot go to T1 also because S1 and T1 are far away. So that's why you don't have the excess of T1 of butadiene just by using light. But you can do the excitation of butadiene by energy transfer from benzophenone, where benzophenone is photoactive. It can absorb the light, gets excited, and then it comes back to its T1, and that T1 is of 69 kilocalorie per mole, which is a bit more than the T1 of the butadiene, which is of 60 kilocalorie per mole. So you have only 9 kilocalorie gap, so it can easily transfer the energy, and that's how you can have T1 of butadiene. Did you get the point?
Yes, sir. But we can use benzophenone then S1 to T1 transition. Why not possible, sir? This one.
Because you have
Benzophenone.
S1 to T1.
T1, yes, sir.
S1 to T1 is ultimately happening, but through the T2, because T2 is
Yes.
of 74. You see, T2 is 74 and S1 is
Yes, sir.
74. They have the same energy level. Did you get
Yes.
it? So that's
Yes,
why
sir.
it will just slide down to T2. Are you getting? And then T2 and T1 again, they are close, 74 and 69. So it can easily come back
Yes,
to
sir.
T1.
Yes,
Are you
sir.
getting? So this, because that is easier, because less energy gap. So lower the, I mean, if you have the energy gaps are very low, okay, then it can easily jump. That we see for vibrational energy levels, changing of vibrational energy levels. It is a similar kind. Are you following?
Yes, sir.
Now let us come to, okay, there are some examples I have given of different other sensitizers which are having triplet state energy here mentioned. Benzophenone 69, you can have acetophenone 74, fluorinone 53. You cannot use fluorinone in this case because 53 is lower than 60. Are you getting? So you cannot have that one because from low to high it cannot transfer the energy. From high to low you can transfer energy. 85, okay, you have 61, 56, you cannot, 53 cannot, okay. So benzyl, so these are different sensitizers we use in different types of substrates, okay, to excite different types of substrates. Now the real chemistry you can see here. So suppose if I take butadiene and do photolysis, okay, so what is going to happen in this case? So this is S0, okay. So you can, if you put light, what you will have initially? Who can tell? You have S1, right? It will undergo excitation, okay. And then what does it mean is, this means is you have the electrons, they are opposite spin, right? S1, are you getting? So pi
Yes, sir.
electrons,
Singlet.
yes. So singlet excited, so they are of opposite spin. So what product you can expect is this 1,3-butadiene got excited, and now you have this one. So two molecule of these can make okay. So you can have okay. Let me tell you. You can have this. Okay, so what we can write is you have a situation. Okay, let me write in a different way. What I can write is this can form so this can happen, okay, because these two electrons, they are of opposite spin, okay. Now they can make the bond. Are you following? This is singlet. Or you can have a situation where you have okay. So in this case, you have the connection between the middle. So you have total 4 electrons. So 2 electrons will be left. So singlet state chemistry here. Let me check. So this is, it will make bond. Okay, so this one you try what will be the mechanism. Okay, it's not
I
exactly
think
coming
that
in.
two bond is opposite, sir. Things are two bond is opposite, that then two spin are connect.
No, you have total 4 electrons, right? 1, 2, 3, 4, and then if you connect one to another, you are having 1 electron
Yes, sir.
available there. That is the thing I'm.
Hmm.
CH2, CH2. Okay, so this one I'll tell what will be the exact mechanism. But these products we can access from singlet state. Okay. Now, when you use the benzophenone, what we have is, you have benzophenone you have used. So instead of having singlet, this is going to have the triplet conformer. Okay. So in that case, benzophenone is becoming triplet and it is transferring the energy. Okay. And you have, these are the products. Okay. These are the products. Got it? Now, here, what you can have, one is, you can imagine you have this is one case. In another case, you can have just the opposite, but both same side. So they can make the bond. Okay, so that is happening for this one, and you can have this one for another situation. You can have these two same, and you can have these two same. So in this case, here you can have bond formation to get this one. Got it? So this is, you have both spin same side, so it is triplet. This is both spin same side. Okay, this is also triplet. So you have the reaction between them. Similar way, here we have the same thing. Okay, so this way you can have different type of products from butadiene. Okay, just by doing photolysis without and with absence, without and with the benzophenone. Quickly, I'll just go through the photochemistry of carbonyl compounds. Okay. Now, just I'll give the basics, and the remaining part I'll be discussing tomorrow. So this is your the electronic states or electron distributions of carbonyl we can find. So you have 2 pi electrons. So you have pi electrons 2. You have non-bonding electrons 4. Okay, non-bonding electrons 4, but one non-bonding electrons is at lower energy states, another is at higher energy states. So you have, if we do the sp hybridization things, if we consider, then you'll understand. I'm not going through that much details, but this one is higher energy state. We can consider this is from P, and another non-bonding will be there. Okay, so this is from SP. SP2 maybe. Okay. Now what we have is that you have n pi star transition. So here, from here to here, transition can happen. So you have this one maintaining the spin multiplicity. So you have, this is S1, opposite spin. Okay. And this one we call it the first excited state, because this energy gap is smaller. And you can have similarly this one, okay, pi star transition. So where the electron can get excited from here to here, okay, maintaining the spin multiplicity. So you have this high energy gap, so this is S2, and that's how we call it S0 to S1 and S0 to S2 transition. They are due to from pi pi star and n pi star. Now reactivity of n pi star, where we see is that you have the n electrons which was paired, it has jumped to pi star, and now n became here a singlet electron. Okay, which is behaving like one alkoxy radical. Okay, and you can have the chemistry obtained from non-bonded electrons on oxygen atom. Okay, so alkoxy radical, it has the reactivity with the non-bonding electrons, pi bonding electrons, and sigma bonding electrons. So what we see is that in non-bonding electrons, it can take one electron and get negative charge. Okay, so alkoxide. With pi electrons, it can do reactions, and you can have polymerization kind of reactions. Okay, and in sigma bond, it can abstract the hydrogen atom, and you can have another radical generation. One more reactivity is that you can have alpha cleavage. So this radical can fall here, and this bond can be cleaved. So you have R radical generation. So this is alpha cleavage. So these are the route we'll also see for carbonyl chemistry. Okay. So here you have excitation. Okay, you have two radicals separated, and then it underwent intersystem crossing. So you have triplet. Now you have two radicals here. It can react with the excess electronic or the non-bonding electrons. So you have this minus. Here you have a radical, so that can happen. Another chemistry is this radical can react with the unsaturations. Okay, alkene or alkyne. So you have this kind of biradical formation, or you can abstract the hydrogen from a sigma bond. So you have the hydrogen abstraction can generate this radical. Okay, alpha cleavage can also happen. You have these two radical, so this can make this double bond having one radical here, and this is one radical. So these are the thing can happen. This is a bit, maybe you can think in this way. You have this bond means you have two electrons. Okay, and if you have this radical, if I put it like this same spin, okay, now what we'll have is that this and this can make bond. Okay, and that is having bond. This can be coming out. Okay, because you have these two are same spin, so you cannot have the bond formation between the same spin. So that's why you'll see the R dot is coming out. You have a radical here. So this is one radical of this radical. You can think in this way. Okay. This way you can have alpha cleavage too. Okay. So these are the chemistry we can access. Intermolecular hydrogen abstraction can happen. If you use the isopropanol, what we'll see is that this keto, it can undergo the excitation, come back to triplet. So you have both same spin. Now this one can abstract this hydrogen. You have a radical generation here. So this is the radical generation from the isopropanol. Okay. So because it is abstracting the hydrogen atom, and now this radical can be combined to give you the pinnacle type of molecule. Okay, so these are the fundamental reactivity of carbonyl chemistry, carbonyl compounds, if you treat with light and suitable reaction conditions. So we'll discuss more about other reactivity in the following classes. We just go through what I have discussed and try to understand. If you have any queries, you contact me and try to clear your doubts. So I'm stopping here. If you have anything, just quickly let me know. Otherwise, we'll stop here. So anything you want to have clarification? Okay, so if you don't have anything, so I'm stopping here. First of all, you go through and then maybe you'll have some doubts here and there and try to contact me. So thanks for attending today's class. Thank you.
Thank you, sir.